Hi, I'm Tim Eastridge with Eastridge Analytics. At Eastridge Analytics, we have a perspective that graph databases like Neo4j should play a critical role in fraud detection and compliance tasks because of their natural machine-readable integration with large language models. Tasks like drafting suspicious activity reports or risk analysts reviewing real-time alerts from the event processor are tedious and error-prone. This is a natural area for large language models to integrate into organizations' tech stacks because it saves time and money. Where organizations are tripping up today is the integration of LLMs with the relational database systems. Organizations are trying to feed too much confusing context into the large language model, and it's causing the AI initiatives to fail. In fact, MIT recently released a report stating that 95% of AI integration projects fail. At Eastridge Analytics, we believe that there's a better way to integrate your data with large language models, and that's through graph analytics. Today, we'll take a look at a demo. Okay, today we're going to look at the IBM transactions for anti-money laundering. This is a data set published on Kaggle.com, which hosts many different publicly available data sets. There are patterns, there are transactions, there are accounts, and we're going to load these into Neo4j graph database to view all of the connections between the different data sets. So jumping over here, I have already run the community detection algorithms within Neo4j to showcase how we can find communities of bad actors like this one. So this is mock data. There's no PII information here, but the green dots represent different bank accounts. The pink dots represent email addresses shared between the bank accounts. These tan dots represent transactions that have been flagged as is laundering equals true. So money laundering is happening in this network, in this community. And lastly, the orange dot represents a phone number that's connected to these two different accounts. So this is a visual representation of the network as shown in the Neo4j graph database. And what we want to showcase today are these two Streamlit apps, which represent a Postgres relational database way of looking at this data compared to a graph analytics approach of looking at this data, and compare the tokens, the number of characters required to send to the large language model, and then take a look at the response provided from the large language model for this task. So jumping over here, we have a typical SQL query, which would join between different tables to gather information that the analyst or the investigator would need to have in order to determine if the activity is suspicious or not. So banks are required to draft suspicious activity reports if there is suspicious activity. And in this case, we can see we have a source ID representing the bank account. We have the person's phone number, the person's email address, and then they're sending money to a different person. So this is the relationship info. So they're sending $31 via cash to this target ID. So the target is this account number. And in row number 2, we can see that these are similar email addresses, Bamboo955 and then Bamboo132, but they're different accounts. They're doing a wire transfer. This happens a few times. So right away, you can imagine this is pretty complicated to understand how these different accounts are connected. We can see that there's some shared similar information between these accounts, but really this is a network problem. And this is why we talk about graph databases and network analytics as very powerful tools to use for fraud detection and compliance use cases. So we have all of this information. We can feed this into a large language model to say, is this suspicious? If so, create a suspicious activity report. We have a prompt here that says, with a limit of 500 characters, create a suspicious activity report from relational database results. The data can contain significant duplication due to multiple joins and complex normalization. The narrative should be clear, comprehensive, and avoid institution-specific acronyms. So that's the prompt. We're just going to feed that and this data to the large language model and have it create a draft, SAR. Okay, great. So now the suspicious activity report has been returned. We can scroll down here and download that suspicious activity report. Next, let's jump over to the network visualization view. So in this case, there are only 4 lines required to write the same query. So we say match this account within this community. We execute the query. It returns a graph visualization. It has 20 nodes and 40 edges. You can scroll down and see a view of the sample data. So this is machine readable version of the network visualization above. So there are different nodes which represent the dots, and then edges for relationships which connect those dots. And the prompt here that we would use is, with a limit of 5,000 characters, create a suspicious activity report, very similar to the prior prompt. Write in clear, complete sentences, spell out each acronym, include dates and amounts, describe the investigation conducted. Basically, we want to include any information that's important for the investigator. So this query is 214 characters up here, 214 characters, compared to this query, which is 2,000 characters. So it's a lot more verbose to gather all of this information together. And the information provided to the large language model is a lot more verbose, because here we have duplicates of the same nodes, if you will, over and over. Versus here, we just have a very concise list of the different nodes and then how all those different nodes are connected via edges. So with that same prompt, we'll generate a SAR draft. Okay, great. So now the SAR draft has been returned. We'll download that SAR draft here. Great. And now we have 2 different summaries from 2 different approaches, all the same information, but given to the large language model through different methods. This is the relational SAR draft, and we can see here the summary of the investigation, the different transactions. This is the SAR draft from the network or graph view. And if you read through these, they're very similar in their output. So the large language model was able to understand the context provided from both mechanisms. But again, the graph method was a lot more concise, both in the way that it was written and the number of characters provided to the large language model, compared to the relational method, which had much more duplication, had much more complexity in the creation of the code. And therefore, what we attempted to prove in this video today is the graph database view is a better way to integrate with large language models, because it's a machine readable mechanism for your large language model to integrate with your proprietary data. Thanks for watching. Please reach out if you have any questions.